So I'm Steve Miner, and we're talking about generating generators today. So first, a little background. If you were here last year at the Conj, I gave a lightning talk called The Way to Eden. That was about my Herbert schema language for Eden. Maybe you've also seen the Clojure West videos. If you were there, John Hughes gave a great talk called Testing the Hard Stuff and Staying Sane. That was about quick check, and that's especially in Haskell and Erlang. And then Reed Draper has ported quick check to Clojure. He gave a talk called Powerful Testing with test.check, and that was also at Clojure West. We also had a hackathon, and Reed was nice enough to help me with some of my stuff. So first, an overview of this talk. I'm going to talk about Herbert schemas again. Some of that might be a repeat for people who were here last year, but there's a lot of new people, so I hope you don't mind. I'll give you a very quick introduction to property-based testing, and then we'll talk about generating generators and how schemas can play a role in that. So, The Way to Eden. That was, I was inspired by Star Trek, and these were the space hippies in that episode. And in this case, they're having a stand-up meeting talking about their Eden project. Okay? So they're concerned with data values. And they've invented the extensible data notation. That's a way of describing your Clojure data. And it also will work for other languages. So that's been a big success. But we're still having problems communicating with the crew of the Enterprise. Okay? So you can see that the Captain Kirk there, he looks like the QA guy who says, you know, I can't test without a spec. You know, it's just like, we're not conveying all the information we need. They don't know how to interpret, right? The words make sense, but they can't put it all together. So Herbert was an insult that the space hippies had for Captain Kirk. Herbert was a minor official who was notorious for his rigid and limited patterns of thought. So I took that as inspiration for designing my schema language. So now, when we're talking about a schema, we're talking about the shape of data. The space hippies have their great ideas, and now that they have a schema, they can communicate better with the crew of the Enterprise. So when we're talking about Herbert schemas, the first thing they're good for is just documentation. This is how I got started. I just wanted a simple notation to keep track of what I was doing with my own code. You know, you come back to it a few months later and you say, oh, what keys was I using here? Did I have nested maps or did I have a vector there? So I developed this notation just for my own use. Once I had a notation, I said, well, if we formalize that, then I could create code to actually validate that my data matched my schema. So of course, like typical programmer, I got a little carried away, started writing a bunch of code about that and made a library, and that's how Herbert got started. Along the way, I said, well, you know, pattern matching is also kind of useful, and I could extract bits of my data by using the schemas. So that was added. And finally, today, we're going to talk about having test.check generators generated from schema. So first, let's review some of the patterns that I use in the schema language. All the literals just match themselves, the keywords, strings, numbers, etc. Symbols in a schema pattern are standing for something else, and we're trying to be intuitive, so int stands for an integer, and kw for a keyword, and so on. So you can think of those as mapping to a predicate that tests, is this item, that kind of thing. Maps, really, in my programming, I think it's really common for most people. You have literal keywords, and then you need to know the type. There's a particular type associated with each of those keywords. So that's how we represent it with a data map that looks similar to the data you're expecting. Vectors, the same kind of thing. So inside a vector, you could have literals, or you can have other patterns. And in this case, I have a vector of first item is an integer, second item is a keyword, and so on. Then you can build these things up. You can also use operators, and or not, and make more complicated patterns that way. We also in Herbert support quantifiers. So this is like regular expressions. The question mark is 0 or 1 of these kind of items, star for 0 or more, plus one or more. And as a shorthand, you can use those quantifier symbols as a suffix on some other kind of symbol. And so that's just expanded into the quantified symbol. And so here's an example. And in this case, we have the keyword. That's just the plain A. Its value should be an integer. The B with the question mark after it means that B keyword's optional. So if B's there, then the value has to be a symbol, or it might not be in my map at all. And C is mapped to a vector of strings. And so then these are 3 examples of the kinds of things that would match that schema. And later we'll talk about how we could generate these kind of examples using the same schema. So you don't have to change the schema. We just say, now generate me data. So the Herbert API is fairly small. There's a few other things, but the main thing is this conforms question mark. Give it a pattern and a value, and it tells you if that value conforms to the schema pattern. If you want to make your own predicate and use it multiple times, you can use conform without the question mark and a schema. That will give you back a predicate function that you can use over and over again. That's kind of the real base of the Herbert schema system. Then I have an example here. So I'm defining my test, and I want to conform to this schema. And you can see that the result of something that does conform is a non-nil value. It's a map of all the bindings. Now, we'll talk about bindings a little bit later, but that schema pattern, the first item in the schema pattern is the bind symbol := since I started programming with Pascal, so that's my homage to Pascal. So I'm binding the K, the capital K, to a keyword, and when we do the match, that capital K is matched the keyword :A. All right, so now we're going to talk a little bit about property-based testing. So my analogy for comparing property-based testing to unit testing, unit testing is somewhat like having a dart, one single dart. I'm going to throw it at a big blank wall, and it'll just hit a spot, and that's my test. Property-based testing is a little bit more like having a dartboard up there and a whole bunch of darts we're going to throw at it. And the second way with the dartboard, that's more fun. And by fun, I mean finds more bugs for me to work on. So test.check is the property-based library that we're going to use. So a few more details on property-based testing. We're testing against randomly generated inputs. And we're going to use a universally quantified property. And we can see a typical example here. We say for all n, which are generated from integers, we want to say that the square of n is greater than the original n. And that sounds about right, but it's not exactly right, is it? OK, so we can see that it's going to fail on 0. And when we get a failure with the quick check, it tells us not only what the failure it found, but it'll also try to shrink the failure case to the smallest possible case that it can think of. That helps you a lot with debugging, because if you get a small test case, you can usually figure out what's going on. If you have a large, randomly generated data structure and something's wrong, your test fails, but you're not sure what part of it to look at. So it's a great feature that you can shrink to the smallest test case. Now, I have a little bit different way of looking at these properties. I also, the typical way to do it is with for all as a universally quantified property. But equivalently, you can think of it as a predicate that holds across all your generated data. And I kind of like the predicate approach because I'm often just writing predicates for myself, using them in preconditions, using them in asserts, that sort of thing. And it encapsulates what I think I know about my data. And then Herbert also will create those predicates for you. So when you're writing your predicate, there's a couple of things you might think about. The simplest thing is just that I do get a good value, right? So sometimes that's a good property just to start with. I'm not throwing, I'm getting a result. But then if you can, it would be nice to have something that narrows it down or has a stronger property One way to do that is to think about having some kind of round-trip consistency. So if you have maybe some complementary functions, you might encode your data a certain way and then decode it, and you want to see that you get the same thing back. Or you might have some other transformations that are reversible, and you want to see that you get the same value back. Another way to think about your predicates is to create a predicate that uses some kind of Oracle or known good implementation. Maybe you have a system that you already trust, and you're working on a new system that's going to be a lot faster, but you want to make sure you still get the same answer. So you can compare your new answer to your old answer and make sure they're the same. So that's another kind of predicate that you might want to write. Now, when you do find a failure, let me go back to when we're shrinking the failures. If you find a failure case, that's a great candidate for making a unit test. All right, you'll make a regression test, save that case, and make sure you don't bump into it again. Because the property-based testing has randomly found that, but that's like gold. Let's hold on to that one and put it into your test suite. Now, a few more details, getting into the properties. The basic macro that you want to use is for all, and that kind of lets you do let-style bindings. So in this first case, the A and the B are both integers, and our property, what we're trying to say is that the sum of A and B is always greater than or equal to the integer A. And that sounds plausible, but then when you think about it a little bit more, but maybe that's not right, okay? So most of my examples here are going to be properties that aren't going to hold across all the generated data. So if B happened to be negative, right, then that proposition will fail, and quick check will tell you, think about these negative numbers. So quick check is the driver that will actually go and take your property and generate all the tests and report the results back to you. So this is the full syntax. Quick check, you can give it a number of trials that you want it to attempt, then you give it a property. And typically, your property is some kind of for all statement. And this is another property that sounds plausible, that the square of an integer, well, let me back up a little bit. In this case, I'm using a generator that's strictly positive integer. So the square of a strictly positive integer is greater than the original integer. And that's not quite true, of course, because strictly positive means something that's not 0, but is some positive number. And it's shrunk immediately to the simplest case of 1. Right? The integer 1 is not greater than the square of 1. There's a little bit something to be careful with when you're looking at the generators that test.check provides. So in this case, the spos int, that's strictly positive integer, that starts at 1 and up. But usually in Clojure, there's also another generator called pos int, which starts at 0. But usually in Clojure, pos doesn't include 0. So there's a bug out there. Maybe the names might change a little bit to conform more to the way we do things in Clojure. But for now, you have to notice the difference between the S at the beginning. That's strictly positive. All right, so we're going to get into more of the details here. But before we do that, I'm going to be talking about generators and combinators. And that reminds me of another Star Trek episode. You might remember this one, The Changeling. The backstory is that there was an old Earth space probe that had somehow merged with a super powerful alien technology. And the Enterprise had discovered this probe out in space. And eventually it comes to threaten the Enterprise and, in fact, might wipe out all of humanity. So does anybody remember what the name of that probe was? People think, okay, yeah, the movie was V'ger, but this is the original Trek episode, okay, The Changeling. So I'm older than a lot of people here, so I remember seeing this as a kid. No, it was called Monad. Do you remember? So, so the Star Trek definition of monad is a super powerful alien technology that doesn't work well with primitive biological units. Okay. So, okay, I hope the Haskell gods will forgive me for that cheap joke. But basically, you don't have to know about monads to appreciate test.check. If you do know about monads, you'll see some things that are familiar. But there's kind of monads under the hood. But you don't have to study them, although they are good to learn. And I am going to learn some Haskell this year. That's on my bucket list. So I'll be getting into monads more later myself. So now let's go to generators and combinators. So these generators come with test.check. They're actually quite a bit more. But the simple kind just generate scalars. So you can think of your integers and strings, keywords, that sort of thing. Return just returns an actual value that you happen to have a hold of. Choose can choose among integers. You can give it a range. There are also generators for collections. And there are some other, the next line of generators, the one of, lets you choose among several other generators. So now we're creating new generators by modifying or taking advantage of other generators. And I don't have time to go into all of those, but it is worth learning and looking through test.check, seeing all the generators you have available there. fmap and bind are really interesting generators. We'll talk a little bit more about them, but so fmap lets you apply your custom function to the result of a generator. So as each item comes out, it runs through your function and creates a new value. Bind takes it another level and creates a new generator from the results of another generator. And we'll see that in a minute. Then there are a couple of new generators in recent versions of test.check that I haven't had too much time to play with yet. But recursive gen looks like it's going to be useful for me for defining recursive data structures. And shuffle will give me different combinations of values out of a collection. And actually, I can use that in my implementation a bit later. So when we're talking about things like bind, and we're generating generators from generators, we have to kind of add, especially for new Clojure programmers, if you're not used to higher order functions, this might take you a little while to think about. You're adding a dimension here to the kind of work we're doing. But it's really valuable and powerful. So take a little time to learn how to use bind and get your head around what it means to bind one generator to another generator. So we're generating values from the first generator, taking those into a function that is going to return a new generator, and then we'll use that generator to give us the actual values that we want. Okay, so there's an example from the test.check. Well, I guess there's an example page on the test.check GitHub repository. It's talking about taking a vector. You want to return a vector and an element from that vector, a vector of ints, sorry. A vector of ints, and then randomly choose one of those values out of that. So you think about that for a minute, and the obvious way to do that with the generators is this expression. So we're going to say, let me work kind of inside out. So at the end of the first line, you can see we say we want a vector of ints. Okay, so we generate those ints. And test.check will naturally start with a small vector and then grow to longer vectors. We're going to modify that by saying we don't want the empty vector. So we say not empty on that generator, and that will exclude the empty vector. So now we're taking bind, taking the result of this vector of ints, feeding it into a function. So this is an anonymous function, but inside that is just another generator expression. And you can see that given a vector of ints, we'll first, as the first element of our tuple, we'll return that vector. That's genReturn just literally returns what we gave it. And we'll say gen elements. Elements takes one of our elements out of some collection. So that will hand you back data, values that look like this. And you can see a small case of first one is just give me a vector of 2 and 2, so we'll just choose 2. And so on. The third one gets a little longer, and we're picking the -5. So that's fine. That works great. And it's worth learning all those generators to do that. Now I want to bring in our Herbert schemas. We're coming back to the schemas we started with. So this is the expression for taking a Herbert schema to do the same sort of thing. And I'll walk you a bit through that. So the HG generator just says, turn my schema into a generator. And the description of the schema directly says, I have the first element is going to be a binding. So I'm going to bind whatever I find as my first element to this capital V. And I'll use that letter later, that local bind name later. The actual element there should be int plus a vector of 1 or more ints, okay, which is what we did before. And then the second element in this tuple that we're returning is something, the in operator on the original vector. Okay. So now the idea here, the goal is that the Herbert schema is closer to your data representation. So you can kind of still have your mind in, what does my data look like? We have a pattern that is written in the same kind of form as the data we want to generate. Okay? And so what I'm trying to accomplish here is that my generators make it easier for you to think about your data and just generate the data without having to go through a lot of effort on the combinators. Okay, and then a couple of other kinds of schema representations that might be easier to use for creating your generators. In this case, we have a couple of optional keywords. And when we get optional keywords, you can think, okay, we're generating now, some of our data will have possibly the :A, it might not, it might have the :B, or it might have neither of them. And you can see some examples of the kind of data we generate from that. So this, to me, is a simpler data representation. That schema there captures what I'm expecting my data to look like in a simpler format than if you write out the longer expression using the typical test.check generators. And because it's a data representation that we're working off of instead of just using our code. Now, the code is great for doing more complicated examples, and you'll need those generators if you have lots of cross constraints within your data. But for a lot of simple things, I recommend that you take a look at how we can generate generators from schemas. Another great example here is just using regular expressions. So if I have a string that's going to match this kind of foobar pattern, but you can see all these variations here that the regular expression gives me. And similarly, for the name of the keyword, I might want to use a regular expression of that. I use a lot of regular expressions in my schemas, just making sure like maybe a word should be capitalized, or I don't want any punctuation characters in a certain field, that sort of thing. And I admit regular expressions are complicated, so we're complicating our whole representation here, but there's probably a good reason for that. Regular expressions are probably the most successful DSL in history. They're very useful, and it's very nice to have them part of my schema language here, and it's great for generators. I want to thank Gary Fredericks at the hackathon at Clojure West gave me the regular expression generator, and that's been really useful, saved me a lot of time. All right, the other feature we have in Herbert schemas is using bindings, and we saw this before. So bindings are useful when you're doing the pattern matching, but they're also useful in the generator that some of the values you want to generate might be based on the previous values that you've seen in a certain data structure. So in this case, we're saying we want to bind the symbol low to an integer that is between 0 and 9. And we want to bind high to something between 10 and 99. We'll package those up into a vector. And then for the rest of our data, we just want to generate one or more integers that are in that range. So I don't think I talked about it before, but for all the kind of numeric types, they're parameterized. You can parameterize them by low and high numbers to establish a range. So then you can see this makes it kind of a little bit easier than doing the bind and the F maps that you might have to do if you were writing things out by hand. And you can see the data that we generate here. Okay, so we talked a little bit about properties before. Now I want to talk about how I get a property from schema. This is the code I use to define a property. And as I said before, I usually think of a property as a predicate and a generator. So I'm going to take my schema, create a generator, and run my predicate over all the values that that generator returns, and I expect that always to succeed or return a true value. So you can see how I hook into test.check. I just call the for all star version of the property generator with my predicate and my schema. And in some cases, you might have a predicate that takes more than one argument, and so then you would give it a schema for each of those arguments, and we'll generate multiple generators. Okay. So anyway, this to me, this kind of fits into the Clojure way of doing higher order functions. If you think about how map works, map takes some kind of function argument and then a bunch of other collections. So the generators here are standing in for those collections. And Herbert check is my wrapper over quick check. And it's the same idea. Typically, I'm going to have one predicate and one schema. And I want that schema turned into a generator. And then I'm going to run that predicate for so many trials. And the hope is that that predicate always succeeds. But if it fails, then I will find quick check will give me back the smallest failure case. So I have an example here where I'm creating a vector of ints. I said int star, so that's 0 or more ints. And my predicate was that the count of that is always positive. But of course, that's a mistake, right? Because the empty vector has a 0 count. So probably I meant to have a different schema there. I meant int plus. But that's the kind of thing. Your schemas are probably going to be more complicated, and your predicates are going to be a little more complicated. But we'll go in and generate the data and find your failure cases. All right, so this function is one that has given me hours of enjoyment. The idea here is when I was working my way to create all these generators, I'm generating data from schemas. I have the schema, and I already had the pattern matching, or the way of confirming that some given data matches my schema. So really what I want to do is say that the predicate I generate from my schema always succeeds over all the data I generate from my generator. All right, and so that's kind of there in the middle. I call the check on my conforming predicate and my schema. I'm going to generate lots of data, and these days now all those generated data all satisfy the predicate just like they're supposed to. But when I first got going, I was finding lots of bugs. Okay, so there you can see this is calling is there towards the bottom, third line from the bottom. Is the Clojure test the main macro for getting a test. And if it fails, if the result is not true, then it will report the error, and I want to report the smallest failure case. All right, so that's kept me pretty busy. I want to say, I'm going to summarize what we talked about. And the first thing is that schemas from the Herbert schemas are Eden data descriptions written in Eden. Okay, so I'm going to describe your Eden data. I'm using Eden to do it. So all your other tools that might manipulate Clojure data structures can also create these schemas. The test.check properties I think of as a predicate plus a generator. Okay, so that's fits into my scheme nicely because Herbert conform with a schema will give me a predicate, and generator with a schema will give me a generator. So now Herbert can help you on both sides of your properties. Maybe the data for your input is complicated, and you want to write a complicated expression using the generator, the test.check generators and combinators. That's great, but maybe your output, your result, has to fit a certain schema. So you could make the predicate on that side. Or maybe as part of your generator, it's easy enough to take bits and pieces of that generator and use a Herbert schema to express that. It might be simpler, but then you have to call some other generators. The Herbert generators are just regular test.check generators, so they can play with all the other combinators that you have in test.check. And so I hope you can take advantage of Herbert schemas and use them in your testing. Now, of course, this is software that's still under development, and there are a few issues, so I have a couple of minutes here. I'm going to just give you some warnings. There's not, probably you're not going to run into these cases, but if you do, just so you know, I'm still working on it, and I'll take bug reports, and I will fix things. The first thing, in my generator, there are some limitations with negation. So a simple case, like not 42 or not any of the simple types, I can generate a generator for that without a problem. But if the generator is a complex generator that maybe I don't know enough about, in the second case here I say not and int and positive. And that right now, that's in a throw. It's in a throw what I call lazy programmer error, because I haven't quite handled that case yet. But you can see the third case works fine, and that's obviously the equivalent if you think about it in logical terms. So what I need to do is get some rewrite rules in there so I can handle more cases. But the truth is, most of my schemas, I hardly ever use conjunction, right? Conjunction is saying I want my one item to match essentially multiple predicates, or when I'm generating, a conjunction says I want to generate a whole bunch of values from one generator, and then a whole bunch of values from another generator, and return just the intersection of those values. So you can see down below, if it's a simple thing like a conjunction of int and not 42, that's no problem. I can compile that into a such that expression and just generate a bunch of ints and check that it's 42. That works fine. But the second example is harder. Generating strings that start with foo and generating other strings that start with bar or that end with bar. And really, what I want to succeed, I wanted things that are both those properties hold. Right now, that doesn't compile into a very good test.check generator. What will happen is such that we'll try so many times and then give up. Right? If you think about what such that is filtering out some bad values you don't want to come back from your generator. So it's unlikely that we're going to ever succeed with that one. And a smarter programmer might have realized that you could combine those regular expressions and get just one regular expression that would do the job, and then everything would work. The final case, I'm saying I want a generator that returns either satisfying the first generator, which is and even and odd, okay, or 42. Now, and even and odd, I know that's not going to work. Just semantically, I have an idea in my head. Even and odd numbers never overlap, all right? But when I'm automatically generating the generator, I'm going to generate something that says, OK, generate me a bunch of odd numbers, and then check that they're even. And so such that will eventually say, hey, I give up. It's not working. I'm not finding anything. And that throws an error when it gives up. Okay? What I think I want, and I'll talk to Reed Draper a little bit later about this, what I think I want is I want that generator to give up but not throw an error. I want it just to be kind of a void generator and give me a chance if I have something like a one of wrapped around that, I can just ignore that bad generator and say, this expression should generate 42, and then I'd be happy. Okay? So those are the kind of things that I'm still working on. For the most part, I don't think you'll even run into those. I'm just warning you that on the generator side, there's a few limitations. All of these examples I listed here work fine for pattern matching. Okay? So I started with pattern matching, and then I said, let's generate for all those patterns. It might have been better if I had thought about generating from the beginning, only allowing patterns that I knew how to generate. But that ship has sailed a little bit. Although we might change and just say, don't do this. Some patterns are too hard to generate. Okay, and then on my to-do list, I have not looked too much at performance. I did get one performance bug, and we fixed that. That was a case where someone had lots of optional keys, and I was originally generating a generator that was a big list of generators with all the subsets of those, with or without those keyed generators. And that turned out just to be too slow, so I came up with another implementation that performs better on those big maps with lots of optional keys. I have an issue right now with nested binding generators. So that's if I do a binding and then use that binding as part of another generator that's doing its own binding. Okay, so if the binding's nested, my generator doesn't work right now. You can have as many bindings that are independent as you want. Those all work. But I have to do a little work to get the nesting right. And again, I don't have too many. The reason this is still a bug is because I don't have too many nested generators in my schemas that I've been testing against, but you could bump into that. The big thing I want to do soon is provide a way to do extensible generators, let you bring your generators into the Herbert schema generator family. And I need to provide a protocol and maybe some utility functions so that you can get your custom generators that you write could play with Herbert. I want to do the Cognitect transit types. Transit is kind of an expansion of Eden with lots of other types. I'll probably do that as a separate project to avoid dependencies. And then the pie in the sky idea, it would be nice if we had a way to debug generators and visualize the output, like what part of my output comes from what part of my generator, or in the case when I'm doing Herbert schemas, some subpart of my schema generated this, or maybe failed to match, and or the generator blew up or something. It would help when debugging to identify the subpart of that schema or generator that was an issue. Right now, if something goes wrong, you'll get a deep error in the test.check generator world, and it doesn't really give you a clue as to how to fix it. So you go back and you got to spend a lot of time kind of staring at your generator combinator expression or at your Herbert schema. And I think we can do better on that, but that might take a while. Okay, before we finish, I want to say thanks. Rich Hickey gave us the Eden format, and he's had a few other good ideas, so I really encourage him to keep going. He's doing a great job. Eric Norman gave me the square peg. He's an open source parser, and that's been really helpful from the beginning of Herbert. Reed Draper did test.check and helped me at the hackathon, and I think he's been really responsive, so I appreciate that. Gary Fredericks gave me the regular expression generator, and he has a project, test.check, that's worth looking at, where he's experimenting with other generators. They might be useful to you. Zach Tellman's collection check was really useful reading, and that caught an important bug that you may have heard about, but you can check that out. And the trekcore.com gave me some Star Trek photos. So if you're interested in Herbert, it's open source. You can reach it on GitHub there at minor Herbert. And my original slide was from the Star Trek II, The Wrath of Khan. That was the Genesis device. All right, thank you.